this work I'll be talking about was largely the brainchild of Matt Haberland, who will not be speaking, but did more than enough work behind the scenes and developing this infrastructure and just talking with me about the talk and stuff to deserve a co-speaker spot. So why a new infrastructure? I think many of you are probably aware of Joel Spolsky's classic article, Things You Should Never Do, Part 1, about what a train wreck it was when Netscape was completely rewritten from scratch and it destroyed them more so than Microsoft or anything. And the idea is old code always has technical debt that's built up, but it also has like knowledge built into it of all different edge cases and things that were handled before. Just things that accumulate over time, like, oh, we have to handle this in this certain way. So to throw something all away and develop something new can be very troublesome. But sometimes it can be very good to do such a thing. I put a QR code here for the issue that Matt wrote proposing this new infrastructure, if anyone wants to take a look at it and see how the sausage gets made, the discussions that go into these kinds of things. Wait, do I have, my slides are not in the order. No, I think it's fun. All right, so one thing that's we all know about is the Zen of Python, if we've ever run import this. And one of the big ones is there should be one, and preferably only one, obvious way to do something. This simplifies the mental model of programmers that there's only one way to do something. You don't have to, like, you can get complexity having to remember multiple API paths and things. Now, is there one obviously way to do things in SciPy stats? Well, there's what's known as a stateless version of a distribution where you pass in distribution parameters. Here you have a norm CDF of 1.3 is like an X, and then you have a mean of 0, a standard deviation of 2. Or you can create what's called a frozen distribution where you freeze this object and you then just pass your X argument to CDF. It gives the same results. So these are different types of objects that are both supported. And now there's a problem here is that there's a lot of complicated machinery that goes into allowing this sort of two ways to do it kind of thing. Now, because you have both the objects instantiated distribution objects, which can then be frozen. All these distribution objects are instantiated on import, increasing import time. There's a documentation scheme which is not flexible, and the documentation can't be specific to certain distributions. Parameters are processed every time because, like, you pass, even with the frozen distribution, it seems actually increasing overhead. And the distributions cannot be freed by the garbage collector due to self-references. Now, the old distribution infrastructure is a miraculous thing. It does a lot of complicated things, but it's also very difficult to work with. And you get bug reports and things where people are like, I want to do this. Well, it's like nothing would get done because, well, we don't want to have to mess with this infrastructure or something, or just we don't have the time to dig into it, and it doesn't have the flexibility. We'd have to change it, but it's like, it's hard to change. So, but a lot of these problems can be solved actually by starting from scratch rather than just trying to work with this thing which was just too complex. And so if you just go back to having one way to do things where families of distributions will be a class, stats.normal, and then you instantiate an object to get a specific distribution, which could also be thought of as a random variable. We'll get to that. And by being able to do this, this introduces a lot of simplifications in the back end that allow us to overcome these limitations that were discussed before. But also, if we're going to be rewriting things from scratch, is the idea, we can try to make other nice changes too. All right, so here's just a demonstration of something that goes on. It's like people think oh, I have to instantiate an object just to compute the CDF of a distribution. But you can look at the times here. This first line here, cell, was computed with the new infrastructure. And you look here at the same call using the old infrastructure computing the CDF, and it's faster because there's work Matt did into caching parameters and not having to do duplicate validation. So it actually makes things faster, which some people didn't expect. There are some changes that were made. New method names. This was something all of the SciPy stats maintainers kind of discussed together, that some of these names, SF for survival function, aren't widely used throughout the entire statistics community, kind of specific to specific parts. It's used a lot in survival analysis in the biomedical field and stuff. But instead of using these, just try to use more descriptive names that hopefully people can be remembered more easily. Just here, standard deviation and variance, just writing it out more explicitly. There's new methods. You have inverse log CDFs and complementary CDFs, log of entropy, mode, skewness, kurtosis, and a plot method that was added for convenience that we'll see. These are just, now sampling works slightly differently. Previously, NumPy had a global random number generator that people would work with NumPy random seed here, or you could pass a random state into the distribution here. It's another way where you have two ways to do things. NumPy moved away from this global random number generator thing because of a lot of problems that it created. So the new way to do things here is you use, in NumPy, is to use generators. This is default random number generator. It can just be passed into the sample method of these instantiated distributions. You could pass in an integer for it, which will instantiate a random number generator. If you don't pass in anything, it doesn't use a global random number generator. It uses the default random number generator. That's standard NumPy stuff. Something I really though, that I really kind of hated using the old distribution. Now parameter shapes are baked into the distribution instances. So before, the old method for sampling was .rvs, and if you had a shape for your parameters, here's a location parameter that has two elements in it, then you notice that the keyword argument to RVS is not shape like you would have for a NumPy array, it's size. That's because it's not really a shape, you would not really work like a shape argument. It has to include the shape of your parameters, which is redundant. And I would always forget this, I know, and get annoyed. But now shapes are baked into the distribution. So this parameter, the mean here, is 2D of this thing. And then when you sample, each sample has shape 3-4 of 2D array, and you get a 3D array result in the way you would expect, and not have to deal with this stuff. Now, there are no distribution-specific fitting methods yet, and it's because the one-size-fits-all approach to fitting that was used with maximum likelihood estimation was very brittle, and it didn't always work, but it was always applied the same to everything, and it would be a source of frequent bug reports where people would just be like, hey, your fitting doesn't work, and it's because it wasn't tailored to the problem, but there was a convenience API.fit. There's no fitting built in yet, but the goal is to create idiomatic, a word here, but an idiomatic pattern or recipe for fitting using the existing SciPy tools because in some cases you kind of want people to have to think about the problem if just doing the default thing every time is liable to break. But you streamline as much as you can, create a recipe, and that hasn't really been done yet, mainly because you kind of want it to be driven by users and use, and let it build up over time and not just create this from the top down, what you expect everyone to do, but it's something. Here's an example Matt wrote of using SciPy.optimize, minimize to fit a Weibull distribution. Like the basic idea is just use existing SciPy tools, but there'll be more development on that. Now I'm going to talk about some cool stuff that's been added, not just stuff that's kind of a replacement for what's there. All right, so there's this, instances of distributions. We could also think of random variables, which are like quantities that follow a distribution. You could have many random variables with the same distribution, and you can do arithmetic operations on them and transformations and things. So here's the very simple one that was added first. Instead of having like loc and scale parameters for everything, you can just shift and scale by doing like arithmetic on distribution, and you can see how that works here. And it produces the same result as setting the mean and the standard deviation there. Other transformations are available. If you want the log normal distribution, that's probably going to be built in, but if you want the log something distribution, instead of having so many separate versions of each thing, like the log this, you can just take the exponentiation of a distribution and get, like, it works as if you're exponentiating a random variable that follows the distribution. So x is normal. What is the distribution of e to the x? That's a log normal distribution, and you can create it with SciPy this way, and it gives the same results to the same accuracy when computing the PDF. I didn't do the times here, but the times are competitive too. Other transformations are available. Currently you can take powers, take a log, you can take an absolute value. If you take the log of something that can be negative, that's not implemented yet because it's complex numbers. It's not, I don't know if that's on the roadmap, but if something doesn't make sense, just don't do it. Now, here's an example of plot in action 2, but here's order statistics. Now, the order statistics of a uniform distribution are beta distributions, and you can take a uniform distribution object here and use the order statistic transform to get a distribution object y here for the order statistics, and then here's a plot of all these different beta distributions and what that looks like. So instead of having to have like separate order statistic distributions of different things, or that can just be baked in for any distribution. Truncation, SciPy used to have like truncated versions of different distributions and stuff and all these separate things, but you can truncate a distribution as a truncated normal. Mixture models, I think, is super cool. And I guess this is going to be cooler when there's better support for fitting them, but you can see here, this mixture model, your random variable is either a normal distribution with standard deviation 0.5 centered at 1 if the coin comes up heads, or centered at -1 if the coin comes up tails, and you can build up mixture distributions. Certain distributions like zero inflated distributions and things can be expressed as a mixture model of like a point distribution, which is just a constant at some point, and like a beta. So a zero inflated beta, instead of having, like someone asks, can you implement zero inflated beta in SciPy? I think there's probably an issue asking for that. You could create it as a mixture distribution. But the old infrastructure has so many distributions in it, and the new infrastructure right now just has normal and uniform. There's more coming. But everything from the old infrastructure can be turned into something in the new infrastructure with this function make distribution. So the Weibull distribution here, you can create the class and then instantiate one. Here's the plot for it. It can do everything from the new distribution. So almost everything from the old infrastructure can already be used with the new infrastructure. So it's not like something that's vaporware which can't be used yet except for a few distributions. Like you could use this for everything in this way, and making them supported natively in the new distribution, new infrastructure can make things more efficient or make improvements in some ways, but this gives you about the performance of the old infrastructure, but allows you to use the new API. Custom distributions. There's always like questions about how to make custom distributions. I always thought it was painful in the old way. You have to subclass RV continuous, and it's I never remember how to do it. It's not something that I would like, oh, I need a new distribution. I'll just create one. We want to make it more flexible for users to create their own distributions. And here's an example of how that looks now, that you just have to create like a small class that has the information that's needed to construct a new distribution, information about the support. This is parameters. I won't go into too much about this. You need to track what SciPy version this is against, because there can be API incompatibilities. And notice here that this only defines a PDF. But methods are vectorized by default. Now here's a comparison here of, we only define PDF, but we're doing a CDF over some big array. Now it's a lot slower than the native CDF based on a formula using the old infrastructure here. But the reason is that this is doing quadrature. It's integrating the PDF, but it's not doing that in a loop over Python objects. It's using the iterative, element-wise iterative algorithms infrastructure that Matt developed to integrate, do a vectorized integration without Python overhead, which is still reasonably efficient, but not as efficient as just using a formula, obviously, because it still has to integrate a function. So the idea here, back into that, we only define PDF, but you get all of the methods through these relations that exist on methods. Matt made this plot. So like you have complementary relationships between a complementary CDF and a regular CDF. Some things you can take a log or exponential to get to, invert, do quadrature, differentiate to go the other way. I think you need to define the PDF though. And all these things like the inversion, quadrature are available in this element-wise iterative framework so that you get efficient implementations out of the box without having to implement everything. It's good to have formulas for the main things, but like the inversion had like the speed is like it only takes about twice as long to do it versus like a C++ in like using a C++ root finding algorithm I wrote for SciPy Special. If you use the framework here in Python, like the speed up is competitive there. Now there's a decision tree for method selection where there's different ways to compute different methods based on what formulas are available and what's defined. And it goes through this tree to figure out what to use. This is all under the hood. Really, it just tries to come up with the best way to calculate something, but the user doesn't have to see this unless they want to, and they can pass in a method keyword argument to run something with a particular method. Something nice that this makes possible is property-based testing, where you can do consistency checks across all the different methods. So there was a problem before where it's hard to test distributions across all kinds of, I guess, all parts of the domain, all parts of the support of things, all kinds of parameter values without having a reference implementation. It's nice to have reference implementations from like arbitrary precision or something, but it's also really good to find bugs, and it worked really well developing this to do consistency checks against these other things. It unearthed a lot of things like calculate a CDF through quadrature or use the formula. It's just, if they don't match up, usually something's wrong, or maybe one method doesn't work so well in some cases, but you can make like skips in the test if that happens, but be aware. All right, so some upcoming work. Infrastructure for circular distributions. There are circular distributions available in SciPy, but they're all just kind of independent things. It's hard to make new circular distributions. It's hard to take an existing distribution and wrap it around a circle to create a circular distribution. So the same kind of principle of making it easy to create new distributions and stuff could be applied to circular distributions. More sophisticated arithmetic on random variables. You could take a sum of random variables instances. If you don't know anything in this case, that's a convolution, but you can compute it numerically and do a decent job. You can special case, you know the sum of two normals is normal. You can override in certain cases where the results are known. Gives more flexibility in defining new distributions. There's still some unsolved problems about what to do if you use the same instance multiple times. X appears multiple times in an expression. Do we model the dependence or not? But support for alternative array API backends is a big one. Having this work with like things like CuPy, PyTorch JAX, being able to take advantage of acceleration and use the same API. This is the infrastructure allows that. It just needs to be, the work needs to be done, but it's set up in such a way that it's not difficult to make those things happen, whereas the old infrastructure would have been very difficult. All right, consistent one way, meaning there's one way to do things, recipe for fitting distributions. I guess the test case there I'm interested in seeing is mixture models, like having it be convenient and idiomatic to fit a mixture model, then you could probably fit about anything and make these things work. But yeah, and then there's a tutorial Matt wrote. I put a QR code if anyone wants to check it out. Gives you the link. A lot of this information from the slides came from that tutorial, but I think it does a good job explaining everything. Acknowledgements, like this wasn't, like, I guess Matt was had the main idea behind this, and him and Pamphile, who's on here, another SciPy maintainer, had this work funded by the CZI grant, SciPy Fundamentals for Biomedicine, but a lot of SciPy maintainers were involved in discussions around the design and development of this. And if you go through that RFC, it wasn't always, there's some people maybe, there was conflict trying to come up with the best thing, but I think that that leads to good results. I think having multiple eyes on things. And I'm sorry if I missed anyone on the list of people I went through that RFC, and because it's been a while since that happened, and tried to keep track of what everyone was discussing. And all right, and thanks. Kind of went through things fast, but hopefully that leaves more time for questions. All right.
All right, so we have a couple of questions and some comments. So I'm going to start with the questions, and then later we'll get to the nice comments if we have some time. So one of the questions by Carl is, do the random variable feature require you, the implementer, to do symbolic computer algebra under the covers?
So that's something that Matt and I have talked about because, it's, in order to do things in a nice way, you kind of have to. You have to simplify expressions and things if something appears multiple times. But obviously, we don't want to make SymPy a dependency of SciPy. That kind of makes a terrible dependency hell of things. SciPy should be fundamental, like at the lower level of things. But I mean, it's either I guess the options are either vastly limiting the support for what kind of operations are available, writing some kind of lightweight symbolic operations that do just enough that we need without over-engineering, or making something like that an optional dependency and making it an optional feature. That's
Good, cool. There's another question by Eric Ma. On the roadmap, will there be support for automatic differentiation of the log PDF and others, or perhaps dispatching to the underlying out-of-the frameworks? It will be great to help unify libraries.
Yeah, so I think this could be, we'd want to write things in such a way where when we have alternative backend support that already supports autodiff, then it can be taken advantage of. Yeah, I have to think, yeah. But yeah, that's definitely something that, I like using the NumPy backend, that's not something that would be done. But for alternative backend support, we would definitely want to write things in such a way that this could be taken advantage of. Like,
we have another one from Jim Pivarsky. Okay, so this one has like a long intro, so I'm going to try to do my best, but I might run out of air. Scaling, shifting, and transforming distributions instead of having many functions is great. But as a user, I want to know if my log of normal, for example, is computed in normal distribution and running it through log, or if it's replacing it with a formula. How much visibility is there into that? If I made a distribution, can I confirm that it's using a streamlined formula rather than transforming on the fly?
okay, so this is something that I had kind of talked with Matt about yesterday, about logging of which methods are being chosen, so that this, like having maybe debug level logging when something runs, where you could see which methods are being chosen, so you know if it's something efficient is being used or if something isn't. That's not in there yet. But another thing is possibly adding metadata to return results that includes information like this, using weak refs and like a function that it gets the weak refs attached to something, was something we talked about. But yeah, that's something that's on the horizon. We want to make it so that you can tell what is being used, because this method dispatch can't be completely opaque. People need to know what's going on under the hood. That's.
All right, I think we have time for one more question. So there's one by Mihai. Can one implement the other method, example CDF, to have them be faster than the default implementation on top of PDF?
Yes. Yes, you can write your own overrides for everything. That's what we actually do when we implement stuff. I just wanted to show that if you just implement some of it, like it won't all be available. But like if your inverse of something is just root finding, then and you have the formula for the forward direction of the function, it will actually be pretty efficient. You don't have to write your own inverse, but like it's good to have formulas for as much as you can get to get better efficiency. Yeah.
Good. Okay, so I'm just going to read the comment so then we can wrap up. So Eric left a really nice comment in the thread that says, less of a question and more of a comment, plus a compliment. Thank you for implementing transformation natively. This will be supremely useful as a tool for teaching people how to think about generative models. So with that comment, I will ask all of you to thank Albert here, and then we'll have later on a break or lunch, probably, one of those. All right, so let's thank Albert.